this part has to be in contact with your bone. Typically, this structure, which is made of titanium oxide, is bio-inert, meaning that nothing happens. You have an interface, you just basically put it in just like a screw, no reaction. So it can break out easily. Can we make the surface conducive to the growth of bone, like silicon? If bone can go on the surface, then you have one integral part. Everything can combine together. Can that work? All right, we'll see. So we actually went on to see if we can make this work. So we combined with nanotechnology. We actually grow some nanostructured titanium oxide. And here, this is a conventional coating with microstructure. This is the new coating with nanostructure. The only difference is the dimension. This is 1,000 times smaller in particle size. Okay? And also, by implanting with hydrogen afterwards, the same process, we put it into blood. And again, we see the growth of something on the surface. And what is it? Again, calcium and phosphorus. So we can actually have bone grow on this coating. So that's very nice because now you put that into a bone, the bone cell will grow on top of that, so we can integrate, adhere a lot better than normal stuff. So that's a real application that we can apply to. So this is just a summary, so we can actually do that. The bone cells can grow on top of TiO2, and it's very nice. We also work on another type of material called zirconium oxide. That's a high-K material used in electronics, also used in optoelectronics. But then we also think, well, can we do it in biology? Typically, when you try to grow this, you have a problem. The interface is oxidized along oxide OH. It's not very good. So, if you look at the infrared spectrum, it's not very good. But we can have a bias. See here, we can apply a negative bias on the sample. If we apply a bias, then this interface can go away. Now, I can give an example. This is the old stuff. Again, high resolution. Silicon atom, zirconium oxide. This is the interface. Not very good. While some bias is a lot better. You can see the very good interface between the zirconium oxide and the silicon. We also look at the annealing process. If we anneal the material, the surface becomes rougher. All right, this is the AFM. This is rougher than that one. And then the bone cells actually grow better on the antipositive one versus the treated one. This is the appetite right here. This is not as good. All right. This is another picture. Very nice. Show the interface between the bone and zirconium oxide. Previously, we have the zirconium oxide and silicon, the substrate. This is actually zirconium oxide and bone. You can see all these nanoparticles right here. This is 5 nanometers, so this is about 2 nanometers wide nanoparticle right in the interface. This is single crystal, not single crystal, well, sort of polycrystalline, and this is the epithelium. Very, very nice. You can actually grow bone also on CrO2, just by the same principle. We also look at cells. All right, so actually cells adhere on the surface with no problem. So the surface is very biocompatible with no problem. I'm going to have 2 more examples. This is something new that we have done. It's called biolabeling. Biolabeling is how you identify the cells. So we use nanoparticles of silicon carbide to try to see if we can have the particles go into the cell and label the cell. This is the dimension of these nanoparticles, very small, about 4 nanometers on the average, size distribution. Okay? And then we introduce the thing in the cells, and you can see these things fluoresce under microscopy. You can see these particles inside the cell. This is the nucleus. All right? So this is very good. So in the long run, what we're going to do is we want to have these particles go into different types of cells. So let's say this is a cancer cell, a good cell, a bad cell, a good cell. And then you can identify, you can see where this thing goes. So you can identify what this cell is. So that's what we call labeling. So that's what we do. So it's just very nice. And compared to the conventional method, this method is more permanent because normally we use organic material. If you go to a doctor, they drink something, you take an MRI, and also take an endoscopy. But here, this lasts a long time because this is organic. Right? And also, this thing is not toxic. There's a lot of work being done on toxicity of nanomaterials. And this is not toxic, meaning that you can have the cell will grow by different doses. You can apply more carbide, less carbide, no carbide at all, and everything goes really well. So this is really nice. So this is the first step. We're going into nanobiology, and that's one thing. Now last, I'm going to show you some really good results that we've done lately. This is on some surgery. This is a patient suffering from multiple scoliosis. Scoliosis is a disease when the spine is curved. Okay, it happens to some people, more women than boys. And then if this is too severe, it presses against your heart and lungs. So your breathing can be difficult, your heartbeat can be a problem. So in the severe case, the doctor has to go in and straighten the patient. What the doctor does is basically go in and straighten the spine, forcefully, and then fold it down. Very traumatic. And if you're lucky, then you'll be fixed like this girl, and the spine will be fine. But there's a couple of problems here. One is the success depends on the skill of the surgeon or the doctor. The doctor is very good, so you get very good correction. If the doctor is no good, then you get under-correction or over-correction. Over-correction could be bad, when you have nerve inside your spine. You can get paralyzed, you can get problems. Is there a better way to do this? Instead of depending on the doctor, is there a way we can have an automatic correction? Is there material that changes shape under different conditions? You're material science, right? Any materials that change shape at different temperature? What is it? Shape memory alloy, right? Beautiful. You all know that. So, meaning that supposedly, conceptually, if you make this thing, this is cold, it's like the curvature of the bed spine. When you go to 37 degrees, your body temperature, it will go straight. So you can use this to control the correction. I have a video here I'm going to show you how this works. This is ice water, okay, cold water. My student put this in, and you can blend it to a different shape. Go back to warm water, it goes back. So that means that, can you use the material, bend it, and then go back to 30 degrees, push your spine back. Beautiful. At the same time, this material is super elastic, meaning that the stress and strain curve is uniform. It bounces back with constant force. Unlike most materials, the more you push it, the more it bounces back. But this material is uniform, even at the end. So that means that the patient, after the operation, just a little bit back, it will push it back. It pushes it back. So it's a constant fixation, constantly pushing it back with the same force. Very, very nice, right? Let me see the concept, how that's done. This is just an artist's conception. The doctor goes in. This is a bad spine, right? And then the doctor goes in, brings some interest, put the rod in right here, cool it down, bend it, and then stick it in the center. All right? Put one more in, warm up, bang, push it back. That's the concept. Isn't that nice? Any problem? Can you see any problem here? 收得稳，收得稳。你这个医生一下子把你升级都可以，那这个 graduate 应该可以。That's not the problem. This is actually better because it's constant fixation. If the patient goes back, it will continue to push you back. Rather than the old surgery, then you go back